Let me get my PowerPoint slide off.
Thank you, ma'am, and thank you all the participants for listening my presentation. Okay, thank you.
Thank you for sharing. All right, our next talk will be by Mohammed from Texas A&M.
Yes.
So, Mohammed,
let me
let you
put
share.
my slides. Okay, let me go full screen.
Perfect. Yeah, we can see.
Okay,
great.
So you can see. Okay. Hi everyone. My presentation is related to themes 5 and 9. It's about DR participation in the wholesale energy and reserve markets and its associated challenges and opportunities. At first, I talk about the type of DR we were interested in, then its modes of operation, and then my research and project part, that is their participation in the wholesale market. Then I talk about the challenges that are uncertainties associated with the resources, cybersecurity and visibility challenges, and the solution that we came up with, that is using a blockchain framework. And last, I will talk about the testbed we are developing in our lab at A&M. The DR that we are interested in is called nanogrid, or also called distributed prosumer. Is technically a building, a residential or commercial building that is equipped with rooftop solar panels, fixed battery energy storage, electric vehicle charging station, and some controllable electric load, like, such as HVAC. These nanogrids can participate in different frameworks. One is participating in the market through aggregation. The other one is participating in the retail market, or providing grid support for distribution utilities, or participating in peer-to-peer energy trading schemes. I will be talking about mode 1, that is participation in the wholesale market. These nanogrids, they are relatively small agents compared to the size of other wholesale market participants. So they need an aggregator or a mediator between themselves and the wholesale market. The aggregator's role is to aggregate their demand, the demand of nanogrids, and participate in the market on their behalf. So the aggregator bids to the market, gets the rewards of energy and ancillary services. Then it can manage the resources of nanogrids through home energy management systems. There are different ancillary services that this aggregator can participate in, but the most general ones are frequency regulation, spinning reserve, and non-spinning reserve. These are procured for different purposes. In our research, we mainly focus on spinning reserve because unlike frequency regulation service, the aggregator doesn't need to be equipped with automatic generation control system, and the dispatch time frame is much larger than frequency regulation. Besides, compared to non-spinning reserve, it's more profitable. Here shows the interaction between ISO or market operator, aggregator, and nanogrids. The wholesale market has 3 major steps: day-ahead market, hour-ahead market, and real-time dispatch. In the day-ahead market, the aggregator, based on its forecast of the uncertain parameters of nanogrids and running its own self-optimizational model, it offers the energy and ancillary bids to the market. Then the ISO, based on the bids of all the market participants and the grid constraints, clears the market. Next, it goes to the hour-ahead market, where the aggregator, based on the rewards it received from the day-ahead market and current status of the in-grid resources, again offers bids to the real-time market, and the ISO runs the market and clears the energy and ancillary services. And next, it goes to real-time dispatch, where the ISO sends the dispatch signal to the aggregator. The aggregator, based on the received signals and the current status of nanogrid resources, schedules the nanogrid resources. This framework has the aggregator needs to, the challenge is to deal with different sources of uncertainty, such as PV generation, electric load, the electric vehicle arrival, departure, and departure time and initial state of charge. Of course, market prices and the temperature, outside temperature that affects the HVAC load. So the solution is to run stochastic optimization models such as two-stage scenario-based, joint chance constraint methods, or robust optimization. Here we, for the first part of the work, we used a two-stage scenario-based algorithm for the participation of this aggregator in spinning reserve and FlexiRAM product ancillary services. FlexiRAM is a product of California ISO that is procured to deal with the uncertainties and flexibility of the market. The long story short, this paper is still under review. The results show that the aggregator can gain high profit out of it, and it shows that it is only 50 nanogrids for our case study. It shows that it can procure up to 1 megawatt of ancillary services to the market, which is a big deal. In another part of the work, we ran a bi-level optimization framework where the uncertainties that I talked about were dealt with by using a joint chance constraint algorithm and the market prices to get a forecast of the prices. We assume that the aggregator can run estimation of the actual market in the lower level. So this bi-level optimization can be converted to a single level mixed integer linear programming. Here we compared our algorithm with some of the algorithms that were published in other papers, such as the stochastic methods, worst-case scenario, and individual chance constraint. The simulation results showed that in terms of computation time, our algorithm works better than scenario-based ones, but not as good as the individual chance constraint because it introduces new binary variables to the optimization. However, as we can see, the ex-ante or expected cost and the realized cost in our case were better, and the results showed the lowest cost in our algorithm. I talked about the uncertainty challenges. Now I want to talk about the cybersecurity challenges. This aggregator and nanogrids, they communicate through Internet of Things, which is technically the internet that we use. And we need to know that these nanogrid owners or this building owner, they are regular people. They are not experts in cybersecurity. So this framework is so vulnerable to cyber attacks. Using the concept of software-defined networking, SDN, and SDN emulators, we modeled the communication system of a single nanogrid and the aggregator data center through Mininet Wi-Fi. We ran the different cybersecurity tests such as network reconnaissance, man in the middle, ARP spoofing, and denial of service through Linux-based software. And these tests were run successfully, which means that okay, I got the text. Can you see the slide and can you hear me?
Yeah, we can hear you. No.
Okay.
Yeah, we let them in. Sorry, when you're presenting, it tells you about that, so you're fine.
Oh, okay, so sorry. So it showed that the system is so vulnerable to these cyber attacks. And next, another challenge that we realized when we were talking with Dr. Alex Pavlexopoulos, He is an expert in practice and market implementation. He said that this nanogrid that we are talking about, they are behind the meter resources and they are not visible to the wholesale market operator or the ISO. And this is a big challenge to implement it in the practice. So what we thought about was to implement a blockchain-based framework to securely record all these transactions that can be used to verify all the energy and monetary transactions offline. I give a little background about blockchain application in energy sector. Blockchain can be implemented in different platforms such as peer-to-peer energy trading, local market, and wholesale market. These platforms can go totally on blockchain, or blockchain can be applied to certain processes such as billing, communication, grid management, and traceability. What we are using it for is to trace the sources of energy and ancillary services in wholesale market. The benefits of blockchain is, I think everybody knows about it because of these cryptocurrencies. So the data are scattered over the network and they're not centralized. The data are auditable, meaning that we can assure that this data are sent by this certain node. They are transparent, everybody can see the data in the network. And they are timestamped, and the update and validation of the data is done automatically through consensus algorithms. There are some challenges. One is that to validate the block, one still needs to download the whole blockchain. The transactions speed is a challenge, and still it needs lots of energy, meaning lots of computers or hardware needs to be connected to the network to validate the blocks, and we still cannot assure the accuracy of the data. And if it's not implemented correctly, there will be some security challenges. Two major characteristics of the blockchain that need to be answered. The first is the privacy, and the second one is the consensus algorithm used for it. In terms of privacy, the blockchain can go totally public, it can go totally private, or consortium means or semi-private. We consider consortium because of its benefits in our framework. First, unlike public blockchain, still permission required to join the network is much faster than the public model, and multiple entities on the blockchain. Participants are known and their identities are revealed, and it has limited decentralization, which people argue that it's a good thing for their application in energy sector. In terms of consensus algorithm, there are tons of them, like in papers and in practice. The major ones are proof of stake, proof of work, and proof of authority. Proof of authority works better for our case since there's no need, unlike proof of work that they need to run, they need to solve complicated puzzles and everything. There's no need for sophisticated hardware, and the reputation of validators or miners is at stake, meaning they're tolerant to 51% attack rule, which means if one has 51% of the resources, they can sabotage the network. It's much faster, and the number of validators is limited. We used Ethereum platform to develop our blockchain. Here shows an example of the a block in Ethereum. Block height shows the number of the block in the chain, and next it shows the public key of the node the data are sent from, and the public key of the node the data are sent to. Next is the nonce, meaning the number of blocks that are generated by that node. And next shows the input data. The input data are based on bytes 32 and hexadecimal. And next is gas use. Gas is the internal currency of Ethereum. It can be converted to real dollars. It shows the profit that the validator gains by validating this block. And next is the transaction hash. It's a encrypted code that is generated automatically, and it includes the data of the current block and the block before it. And next, here is an example of the data that needs to be recorded for the nanogrid to aggregator communication. It technically is the parameters and the current status of the different resources such as battery, PV, load, and electric vehicles. This one is an example of the data that needs to be secured, recorded when aggregator communicates to the nanogrid, which is which are the operating state and output power control commands for different resources. This is the last slide. It shows that the test bed that we are developing in A&M. We're gonna model the distribution grid in Opal RT, real-time simulator, and we're gonna model a single nanogrid in Typhoon HIL. And the aggregator or the optimizations are run through in cloud server, and all the transactions that I talked about will be recorded in Ethereum-based blockchain, and using the smart contracts developed in Solidity programming language. Thank you. My presentation is over. I will be happy to answer any questions if you have.
All right. Thank you very much. We do have one question here. Sorry, I'm hearing an echo. All right, so Ethereum platform is highly inefficient, and recent news informed us of consuming power equivalent to small country. Are there other platforms that you might be able to use?
Here is like it's a misunderstanding. Ethereum, the one that is used as a cryptocurrency, is different with the private node of Ethereum. A private node of Ethereum, you can implement this separately. Is totally different than this Ethereum that is used for cryptocurrencies. So I think the power consumption of it would not be a problem. Besides, you can implement the proof of authority algorithm, which doesn't need sophisticated software to validate these blocks.
Okay. What is the maximum? What are the maximum and minimum values of power exchange needed to participate as an aggregator in wholesale? Is it 1 megawatt? How do we get to that value just with nanogrids?
Yes, that's a good question actually. There's no maximum power, so like there's this power plant that generate 1 gigawatt. But there's a minimum. The FERC Order 2222 that mandates the markets to provide the opportunity for these aggregators to participate in the market. It says 100 kilowatts. So this nanogrid, their power range is between 1 kilowatt to 5 kilowatt for the residentials. For the commercials, it's much higher. And this aggregator is aggregating their demand and parties. So assume that it aggregating like 1,000 of them, so it easily can meet the minimum requirement. And this minimum requirement of current minimum requirement of 1 megawatt is, it depends on the market. In ERCOT is 1 megawatt. In California ISO, it was either half megawatt or 100 kilowatt. I'm not sure.
So, so I guess one of the things, as you talk about the nanogrids, some of that will be dependent on the state regulations and other regulations, as well as federal and international regulations related. Correct?
Yes, that's a big challenge. I mean, the regulations are like stopping them from. I know that like PJM doesn't like this distributed resources participation in the market. The same is with ERCOT, but California ISO is much more progressive on that.
Yeah.
Well, I think the aggregator create. Oh, go ahead.
Sorry. Yeah. So the one issue, I mean, I don't know how exactly we can put it in place for the field side, because the theoretically we can do, as long as like we meet the minimum requirement of 100 kilowatt or 1 megawatt, even we can go up to 1 gigawatt, not 100 gigawatt. So, but how do you see the challenges when you really wanted to get an aggregator from different customers? What are the challenges you come across, or maybe the literature already covered it? Can you please
Sorry, I couldn't quite understand your question. Can you please repeat that?
Okay, so I mean to say, how do you see the challenges when you really implement in the field? I mean to say, accumulating 50 customers from different background or different lifestyles. So then how do you see the execution of this nanogrid as aggregator with the wholesale market or with the any retail market? So
Well, that's a good question. We don't have their like the implementation of them in practice. Definitely, there will be more challenges that the ones that I mentioned, like modeling these uncertainties. It needs large of historical data and probabilistic analytics. This is one issue. The other issue is these cybersecurity challenges. People, these nanogrid owners, they need to be trained and learn that how to improve the cybersecurity of them. And besides that, regulations that Dr. Scholz mentioned. For now, this FERC Order 2222, it assigns this coordination between the ISO, the distribution utility, and these aggregators. It assigns it to themselves, and it says that you need to figure out how you're gonna collaborate on that, which is a big complication in here. And it's a forwarding step, but it's not like this is done and this can be implemented. There are many issues with that.
yeah, thank you. And then the last one is, who will be playing an aggregator role here? Who will be the agent, or maybe who will be the person coordinating with the aggregator, as well as who is the coordinator in this?
The aggregator will be a third-party entity, and for now there aren't that many aggregators. This is a work that Dr. Alex was working on too, and the agents are these nanogrids, and it will be so that the nanogrid owners wouldn't be involved that much, because their resources will be controlled automatically through aggregator, and the aggregator is a third-party entity that should be introduced to the power grid.
Thank you.
You're welcome.
All right, we've got time for one more question, and it's in the chat. Did you model actual participation in WEM?
Here's if I understand that they mean running an actual market. If this is the question, it's another challenge, because this wholesale market, the ISO runs multiple processes there, but we assume that three major processes of it. One is day-ahead market, the participants bid to the market, and the market operator clears the market, then the hour ahead, then the real-time dispatch. And we simplified them because we didn't consider all these security, such as N-1 rule and like security concern unit commitment.
Great. Well, thanks, Mohammed, for your talk. If you could put the title and your name and email in the chat for others that may have questions after. So thank you so much.
You're welcome.
All right, let's get